Sometimes a visitor slips quietly across the edge of our sky, reminding us that our solar system is not sealed but open to a wider road. A faint interstellar object arrives from beyond the sun's most distant comets, following a path that bends once and then escapes forever. We give this traveler a name, because naming is how we begin to follow its story through time. We ask a question, the kind astronomers always return to. What is it? Where did it come from? And what can it teach us about the birth of other worlds? Welcome to the Drowsy Astronaut. Here we drift deeper into the cosmos while gently setting aside the burdens of your day, so the mind can slow and the heart can rest with distant rhythms. You may relax or even fall asleep while your subconscious listens to the passage of a new interstellar traveler, a small active body called 3L Atlas. So let's begin this journey and follow its path step by step, moving slowly from first sight to deeper meaning. On the 1st of July, a telescope in Chile noticed a faint point sliding across the crowded sky, and software trained for wanderers flagged it at once. The facility belonged to the Atlas program, which scans wide fields every night and catches things that do not sit still. Earlier frames gave pre-coveries, hidden images that had captured the point before we knew to look, and together they stretched the arc of motion into something certain. From that longer arc came a conclusion almost no one expects to make. The orbit was open, the speed too great, the body not bound to the sun. Interstellar is a precise word here. It means the fitted orbit is hyperbolic, with excess speed that gravity cannot bind. A bound comet traces an ellipse, a curve that repeats like a season, while a visitor writes a hyperbola, a line that bends once and leaves forever. You can picture a marble rolling inside a bowl. Slow ones stay circling, fast ones skim the rim and fly away. That open path is the mark of another star's nursery, a birthplace far from our own, carried to us only by chance. Names in astronomy often look like codes. They compress discovery, type, and sequence into a handful of letters and digits. For public clarity, we call it 3L Atlas, a steady syllable easier to hold in the ear than the official string. What matters is that the label marks it as the third confirmed interstellar traveler. It shows a bright coma, the fog of dust and gas that lifts when sunlight warms ices near the surface. Think of a kettle on the stove. Nothing at first, then thin threads of steam, then a strong plume once heat reaches the right threshold. A comet's nucleus is a cold core, darkened by crust, awakened by sunlight that seeps only a shallow depth. Carbon dioxide is the quick gas. It leaves easily at colder temperatures, while water waits until the lamp grows stronger. From that shifting balance of gases, we read a thermal script, a record of layers written long ago in a different system. Safety is the question most people hold quietly. Will it come near Earth? Could it pose any threat? The orbit gives a calm answer. The distances are wide, and the geometry never crosses our lane. Closest to the Sun, it will swing inside the orbit of Mars, but never closer than 170 million miles from Earth. So the only real impact here is on our understanding, which is the best kind of impact to hope for. Brightness is practical rather than poetic. The traveler is faint, a subject for telescopes, not a spectacle for city rooftops. In deep images, a teardrop glow surrounds the hidden core, with a tail stretching away under the push of solar light. We cannot see the small nucleus directly, but we infer its size from brightness and dust behavior. Early estimates suggest a range of a few hundred meters to a few kilometers, large enough to endure, small enough to hide inside its own ville. Motion is another anchor, measured night by night against fixed stars. The drift becomes a speed, and when fitted to gravity, it shows an excess well over 100,000 miles per hour. That speed is a fossil memory, preserved from the ancient push that ejected it from its birth system. Perhaps it was flung by a giant planet long ago, perhaps by the tide of a passing star in a crowded nursery. Direction adds context, for it enters from the backdrop of Sagittarius, rich with the crowded Milky Way. For observers, this is both a gift and a challenge, a beautiful field thick with stars, but a difficult canvas to subtract. Space telescopes track the comet itself, letting background stars streak into lines while the subject holds sharp. Ground telescopes often track the stars, leaving the comet as a faint smear sliding across the frame. Dust is thinner than breath, but it builds structures millions of miles long. In the coma, each escaping grain reflects sunlight, each adds to the glow, though the density is far below any air we know. The tail is a sculpture of particles, carried outward, sorted by size, painted against the sky. When you see such a comet, you see sunlight scattered, not solid form, a painting more than a portrait. Soon, the object will reach perihelion, the turning point near late October. There, sunlight will push the nucleus harder, releasing more gases, driving brighter jets. Afterward, it will fade, receding outward, the coma thinning, the tail stretching into a memory. By December, it will still be visible, but fainter, a guest already on the way out, already writing its farewell. Comparison places it in a short lineage alongside Oumuamua and Borisov. One looked like a puzzle, dry and strange. The second looked like a comet from our own catalogue. This new body is an active comet too, but with a chemistry tilted toward carbon dioxide. 3 cases make a pattern, a first sketch of what distant nurseries may send across the dark. Listen for the underlying rhythm, discovery, confirmation, chemistry, safety, and meaning. We measure light, we compare it to what we know, and we infer composition and history. Each new visitor is a bead on a necklace of knowledge, strung patiently over years. This one small speck is a fragment of another star's history, offered to us only once and never again. Let's drift quietly toward another small corner of the cosmos, carrying the image of that teardrop glow against streaked stars. The path is open, the speed is high, the nucleus small but active, the coma growing with time. Late October brings the turn, December another chance to see, and then the long goodbye beyond our sight. And somewhere beyond the edge, this traveller will keep going, a messenger we met briefly, then lost to the wider road. Perihelion is the milestone ahead, the place where this traveller will come closest to the sun, and with that closeness comes both heat and revelation. At roughly 1 1/3 astronomical units, this distance is modest compared to many comets, but it is still far enough to keep Earth entirely safe. The important thing about this approach is not the danger, but the chemistry, because sunlight at that distance is strong enough to wake different layers of ice. From this awakening comes a sequence, the order in which gases emerge, and the order tells us about how the nucleus was built in a faraway system. Carbon dioxide has already spoken first, revealed even while the comet was still far beyond the orbit of Mars, a sign that this volatile lies near the surface. For most of our familiar comets, water dominates once they approach the inner system, but here CO2 rose strongly long before water joined the flow. That difference becomes a signature, like the accent in a voice that tells you where someone grew up. And this accent points to a nursery colder than the region where most of our comets formed. If 3L Atlas holds its CO2 strength, even near perihelion, then its birthplace must have been beyond the CO2 ice line, a colder belt in a protoplanetary disk. Think of a freezer shelf for an analogy. Water ice sits on one shelf, carbon dioxide on another colder shelf farther back. Comets that formed closer in mostly carry water ice as their first voice when heated, but a comet built on the farther shelf speaks in CO2 first. This is how astronomers translate a coma spectrum into a history lesson. Every line of gas is like a word in a diary left billions of years ago. The remarkable part is that this diary has crossed light years, and yet we can still read its entries simply by splitting sunlight into colors. Water will not stay silent forever. As perihelion draws near, deeper heat will reach the reserves that take more energy to lift. When water joins the flow, the balance of gases in the coma will shift, and that shift can be tracked night by night with telescopes. If the ratio of CO2 to H2O remains high, the comet tells us its outer layers preserved carbon dioxide more than most. If the ratio tips, we learn that layering runs deep. In either case, the lesson is clear. Other systems store their ices differently, and that difference becomes visible only when one of their fragments passes by our sun. Dust adds its own voice, and that voice is textured, because grains scatter light in ways that reveal size, shape, and porosity. When light waves bounce off dust, they return with a small twist called polarization, and the depth of that twist changes with the angle of sunlight. At last shows a polarization curve deeper than we expect from many solar system comets, which hints that its grains are fresher, more porous, or less processed by heating. Think of ash compared with pebbles. Both scatter light, but ash makes a softer glow and pebbles make a harder glint. Porosity is critical because porous grains let gases seep through them easily. Compact grains resist, and the difference shows up in the coma's shape. If Atlas carries grains like loose snow, then sunlight can drive gases out smoothly, carrying particles into a wide halo. If grains are more like stone, gas struggles to lift them, and the coma looks thinner and more confined. Early data favor a more fluffy texture, which means this comet is probably a pristine survivor from a cold nursery, not a body baked repeatedly by close passes. Rotation governs the rhythm of activity, because as the nucleus spins, different regions face the sun, vent, and then fall back into shadow. Astronomers watch for brightness waves that repeat with hours or days, and those waves mark the spin period. Once the spin is known, we can model jets more accurately, because jets add tiny pushes that nudge the orbit slightly away from pure gravity. These pushes are called non-gravitational terms, and though they are small, they add up, refining our understanding of the comet's path. Tail mechanics are another chapter in this patient reading, for the tail is not one structure but a sorting ground. Small grains behave like feathers, caught quickly by sunlight pressure and swept far downstream. Larger grains are like stones, harder to move, staying close and thickening the near tail. By fitting curves called synchrones and syndines, astronomers can map which grains left when and how large they were. Comparison with past visitors is unavoidable, because only 3 are known so far. Oumuamua was a strange shard with no obvious coma, yet a mysterious acceleration as if something subtle pushed it. Borisov was a classical comet with a tail and coma behaving much like the comets we know from our own system. Atlas now joins as a more unusual cousin, a comet with strong CO2 activity and grain properties that appear different from most locals. 3 cases do not yet define a population, but they begin to sketch possibilities. If future visitors resemble Atlas, we may conclude that cold, CO2-rich nurseries are common in the galaxy. If they resemble Borisov more often, then interstellar comets may be familiar in most ways. Oumuamua will remain the outlier. the one that told us diversity runs wider than we guessed. Risk has been ruled out from the start. Wide distances mean no threat to Earth or planets. This allows us to focus entirely on measurement rather than alarm. With perihelion at 1.4 astronomical units and closest Earth distance at 1.8, the geometry keeps us calm. The real impact is on knowledge, and that is the most valuable outcome. Direction of approach adds beauty and difficulty. The object crosses a background crowded with Milky Way stars. For observers, this is both a gift and a challenge, because the backdrop is lovely but crowded. Space telescopes track the comet itself, letting stars streak into trails, while ground telescopes often track the stars, leaving the comet blurred. Both modes are useful because each reveals different aspects of coma structure and motion. Brightness is not steady. It rises and falls as new vents open, and watching those changes is like reading weather across the surface. Jets that flare produce arcs in the coma, small fans that later spread and blend into the halo. If vents are localized, the coma becomes lopsided, tilted toward the side with strongest emission. By stacking images over weeks, astronomers can see these asymmetries clearly, building a map of the hidden surface. Fragmentation is another possibility to consider, because comets under thermal stress sometimes break into pieces. If Atlas were to shed a fragment, astronomers would track both bodies, learning about internal strength. Even a small breakup would pose no risk, but it would offer a rare chance to compare two fragments of the same interstellar visitor. Comet fragmentation is like a cross-section, nature splitting the object to show layers we cannot see otherwise. Analogy helps again. Think of a loaf of bread under a crust. As heat seeps in, steam pockets form and push outward, and cracks release jets of vapor. In a comet, the crust can resist until pressure builds, then fracture suddenly, releasing gas and dust in a burst. Such bursts make the coma pulse, and by timing them, we infer internal pressures and strengths. Spectra tell us not only which gases flow, but also how they change with distance. The strong CO2 signal at large range already sets Atlas apart. Later spectra may reveal water lines growing stronger, or even more exotic species like CO or methane. Each identified line adds a word to the story. Each ratio adds a sentence about formation conditions. Polarization curves are equally rich in meaning because the shape of the curve tells us about dust texture. A deep negative branch at small angles often signals fluffy, porous grains. If Atlas continues to show such a curve, it means its grains are younger or less compacted than many local comets. This detail becomes a benchmark because it lets us compare dust processing across different stellar nurseries. Population modeling grows from these detections. 3 in a decade means interstellar wanderers are more common than we once thought. Surveys like Atlas are nets, and the finer the net, the more visitors we catch. Each new catch adds to our statistics, and statistics build a truer picture of how common ejected debris is. Origin cannot be traced to a specific star because gravitational nudges erase the path, but we can speak of zones. This object likely formed in a cold belt beyond the CO2 ice line, preserved in deep freeze until ejection. That ejection may have been caused by a giant planet in its system, flinging it outward, or by a passing star. What matters is that the body was released long ago and has been wandering ever since, until chance brought it here. Rotation, once known, will refine these pictures even more. If the spin is fast, stresses may build quickly, risking splits as jets torque the body. If the spin is slow, activity will be smoother, with vents staying sunlit longer before dark. Either way, the clock of rotation guides the rhythm of gas release. Safety comes not only from distance, but also from predictability. By tracking the coma and jets, we can calculate tiny non-gravitational nudges. With these terms included, the orbit solution becomes more stable, ensuring we know where the comet will be far into the future. This stability lets astronomers relax, focusing on chemistry and physics rather than navigation worries. Comparison with local comets also sharpens perspective. Most of ours are mixtures of water, CO2, and dust, but with water often dominant. Atlas tilts towards CO2, which makes it interesting as a contrast. If more interstellar visitors share this tilt, then we learn diversity is the rule, not the exception. Dust models will refine as more images arrive. By measuring coma brightness at different wavelengths, we can infer grain sizes. Small grains scatter blue light more efficiently, large grains favor red, and the balance shifts with time. Such color shifts become a clock, telling us when different dust populations left the nucleus. Lesson by lesson, the comet unfolds. Each gas line is a sentence, each dust curve a paragraph, each spin pulse a rhythm. Together, they make a chapter in the new book of interstellar comets. This book is still thin, but every page thickens our understanding of how planets form elsewhere. Later in the season, the comet will emerge from behind the sun. Observations will resume, and we will compare outbound activity with inbound. Symmetry or asymmetry will speak of layers, of whether heating opened new cracks or left the nucleus unchanged. These comparisons are gold because they show how heating sculpts a body in real time. For now, the traveler is teaching us patience. Data arrive nightly, each frame a small dot that joins the growing story. The dots become an orbit, the spectra become chemistry, the coma becomes structure, and in each step we are reading a fragment of another world's past. Comparison is the next natural step, because to know what is unusual, we must hold it beside what has come before. So far, humanity has measured only 3 confirmed travelers from other systems: Oumuamua, Borisov, and now 3L Atlas. Each arrived by chance, each was tracked carefully, and each revealed a different face of how small bodies are built. Taken together, they form the first sample of interstellar material ever studied, and even 3 are enough to show surprising diversity. Oumuamua was the first, discovered in 2017 by the Pan-STARRS survey, a faint, elongated object rushing inward from the direction of Lyra. At first, it looked like an ordinary asteroid because no coma or tail could be seen, only a point of light moving swiftly. But when its orbit was solved, the truth was clear. It was not bound to the sun. Its path was hyperbolic, and its speed marked it as interstellar. That realization gave it a title as the first interstellar object ever confirmed by science. Oumuamua puzzled astronomers because it showed no obvious coma, yet its motion drifted slightly as if a gentle push was at work. The likely cause was outgassing, but if gases escaped, they were too faint to be seen with telescopes. Some proposed exotic ideas, from hydrogen ice to nitrogen ice to even artificial origin, though none are proven. What remains certain is that Oumuamua was a fragment, perhaps chipped from a larger body, perhaps ejected during chaos in a young system. Shape became another debate because its brightness varied dramatically as it spun, suggesting an elongated or flattened form. Models gave either a long cigar shape or a wide pancake shape, both unusual compared to known asteroids or comets. No spacecraft could reach it in time, so its details remain hidden, known only from a short window of observation. Oumuamua remains the enigmatic one. silent in activity but strange in shape, leaving more questions than answers. Borisov followed in 2019, discovered by an amateur astronomer with a small telescope in Crimea, and quickly confirmed as interstellar. Unlike Oumuamua, Borisov behaved like a normal comet, with a clear coma and a long tail shining across the sky. Its spectrum showed water, carbon monoxide, and other familiar volatiles, making it look very similar to comets of our own solar system. In some ways, it was the reassuring one, proving that other stars can make comets just like ours. Dust from Borisov was also unusual in subtle ways. Polarization studies showed grains that were fresher, more pristine than typical solar system comets. This hinted that it came from a nursery less processed by radiation, a body still carrying the texture of its original disk. The combination of a normal-looking coma and a pristine dust signature made Borisov the classic, but also the youthful one. It confirmed that some interstellar comets are very much like the icy wanderers we know well. Atlast is the third, discovered in 2025 by the Atlas survey from its Chile station, and already it shows traits unlike either of its predecessors. Like Borisov, it is a true comet, with a coma and dust tail seen clearly, proof that ices are sublimating. But unlike Borisov, it shows strong carbon dioxide at distances where water should be faint, making it chemically distinct. Its dust polarization curve also appears different, pointing toward grain properties that set it apart from both earlier visitors. 3 objects, 3 personalities: the dry shard, the classic comet, the CO2-rich traveler. What this teaches is that diversity is the rule, not the exception, even in such a tiny sample. If every new visitor looks different, then the galaxy's nurseries build small bodies in many ways. That thought is powerful because it reminds us that our solar system is not the template, but just one variation. Oumuamua came as a whisper, faint and strange, leaving quickly. Borisov came as a bold signature, bright and cometary, more familiar. Atlast now comes as a blend, cometary like Borisov, but with chemical quirks and dust textures all its own. This progression tells us that the spectrum of interstellar bodies is wide, spanning dry fragments to gas-rich comets. Each detection moves us from anecdote to pattern, building the first outlines of a population. Think of meeting 3 strangers at random in a city. One is quiet and puzzling, one is familiar and warm, one is familiar yet odd in detail. From just 3 meetings, you can guess that the city is diverse and that no one type represents the whole. So it is with Oumuamua, Borisov, and Atlast. 3 encounters, 3 very different impressions, and behind them must be countless others, drifting unseen through the galaxy, waiting for us to cross their paths. Comparison at a deeper level comes from chemistry. Oumuamua showed no visible coma, so its chemistry stayed a mystery, with only indirect hints from its acceleration. Borisov showed water and carbon monoxide, a typical mix for solar system comets, though with unusually pristine grains. Atlast shows a CO2-heavy mix, rare even among our comets, suggesting a colder nursery of origin. Dust adds another layer. Oumuamua gave no coma, so no dust could be studied. Borisov gave polarization curves that spoke of fresh grains. Atlast gives curves that hint at porous aggregates, unusual compared to most comets here. Shapes, too, differ strongly. Oumuamua was elongated or flattened, extreme by any known standard. Borisov was a more typical nucleus, small but not extraordinary in shape. Atlast's nucleus remains unseen, but estimates put it within a modest range, likely rounder than Oumuamua but still cloaked in gas. Lessons emerge slowly. Oumuamua showed us that interstellar fragments exist and can be strange. Borisov showed us that many interstellar comets are familiar. Atlas shows us that composition varies widely, especially in the balance of ices. Together, they teach that interstellar bodies are not one type, but many. Science moves from case to case, weaving a bigger picture. The first case forced us to expand our imagination. The second reassured us with similarity. The third stretched chemistry again. This back and forth is not confusion, but growth, because each object becomes a data point in a larger distribution. The future will bring more, and with more, the picture will stabilize into a clearer story of diversity. Population models now assume that many such objects cross the solar system every year, most too faint to notice. With wide-field surveys, we are beginning to catch them one by one. The discovery of 3 in less than a decade means the true number is high, and our instruments are only now sensitive enough to find them. Future surveys will expand the sample, and comparisons will grow stronger. Technology will also matter. We cannot send spacecraft to each visitor with current rockets. They move too fast for intercepts launched after discovery. But missions may be planned in advance, waiting in orbit to chase the next interstellar target. Such missions would return direct images, direct dust samples, and data beyond what telescopes can provide. Future dreams include capture missions, though the speeds make them unlikely for now. Instead, flybys will be the goal, glimpses up close as the body speeds past. Even a brief visit would answer questions that telescopes cannot. Nucleus shape, jet structure, grain sizes seen in situ. Until then, comparisons rely on light, the patient reading of photons. Perspective also matters here. In the early 20th century, no one had ever confirmed an exoplanet. Now we know thousands, and diversity is the rule. Hot Jupiters, super-Earths, mini Neptunes. So too, it may be with interstellar objects, a wide spectrum of shapes, sizes, and chemistries. 3 are just the start, a prologue to a library that may one day hold hundreds. History may record Oumuamua as the enigmatic first, Borisov as the classical second, Atlas as the diverse third. But each carries equal weight, because each expands the definition of what interstellar debris can be. Astronomers will cite them together, compare them together, and build theories tested against all 3. And each new find will either reinforce or challenge the patterns we see so far. Imagine the Milky Way filled with countless comets and fragments, each ejected during violent early years of planet formation. Each one is a messenger, carrying chemistry from its birthplace, drifting for ages between stars. We see only a few because our tools are limited, but each sighting proves that many more exist. The galaxy is likely crowded with these messengers, silent until they pass near a star and wake again. Patience is the virtue astronomy teaches best. Oumuamua stayed visible only for weeks, Borisov for months, Atlas for perhaps longer. Each time we learn a little more, but always incomplete, always with unanswered questions. And so we wait for the next traveler, and the next, until patterns grow sharp enough to trust. 3 visitors, 3 lessons, 3 ways of being interstellar. 1 silent, 1 familiar, 1 chemically distinct. This is the story so far, and it is only beginning. The sky will bring us more, and each will add a new chapter. Let's drift slowly into another corner of this long narrative, carrying the memory of the dry shard, the classic comet, and the CO2-rich traveler. The meaning is not finished, the pattern not complete, but the journey has begun. Next, we turn toward the peak of Atlast's activity at perihelion and watch how its water and dust join the carbon dioxide already in flight. From there, we will see whether its chemistry converges toward the familiar or remains tilted toward the cold nursery of its birth. Perihelion is not just a date on a chart, it is the turning point when sunlight is strongest and a comet's secrets are most likely to surface. For 3L at last, this will happen at about 1.4 astronomical units from the Sun, closer than Mars, farther than Earth, a middle ground of warmth and safety. Though the distance is comfortable for us, the intensity of solar light is still triple what it was out by Jupiter when this object was first noticed. That extra heat is what wakes new ices and drives new jets, the real test of how a comet is built. Water is expected to rise now because its sublimation threshold is finally crossed. Earlier, we saw mostly carbon dioxide as the dominant gas, but perihelion is when water vapor should swell into the coma. The balance of water to carbon dioxide is a critical ratio, one that astronomers measure carefully with spectra. If water remains low, the lesson is that this comet's layers are unusually rich in carbon dioxide, unlike most we know. Think of a crusted hillside touched by spring sun. First, the thin frost melts, then deeper ice seeps out, and streams grow. In comets, carbon dioxide is that thin frost, quick to release, while water is the deeper reservoir waiting its turn. Once water begins to flow, the jets grow stronger, carrying heavier dust grains and altering the shape of the coma. This shift marks a new phase of activity, and the timing of it is one of the most important things astronomers want to track. Dust responds differently depending on grain size. Smaller grains are like ashes lifted easily, streaming far into a diffuse halo. Larger grains are more like sand, heavy enough to hang near the nucleus before drifting slowly. By measuring brightness in different colors, scientists estimate which sizes dominate at perihelion. Jets are not smooth fountains but patchy exhalations, venting from active spots where cracks or layers are exposed. If the comet spins, those vents sweep like a slow sprinkler, modulating the coma's shape over hours. Sometimes vents emerge suddenly as new fractures expose fresh ice to sunlight. Such outbursts can brighten the comet by an entire magnitude overnight, surprising observers who track it. Rotation governs these rhythms because the spin period sets the timing of sunlight exposure. If at last spins quickly, vents open and close in rapid cycles, creating flickers of brightness in the coma. If it spins slowly, one side may stay sunlit for long hours, producing more steady flows. Astronomers study the light curve for repeating patterns, clues that reveal the hidden clock of the nucleus. Stress builds as gas escapes unevenly. One jet may push harder than another, creating torque. Over weeks, torque can shift the rotation axis, changing which regions face the sun most often. This is how comets can evolve even over a single pass, adjusting their orientation like a ship in a changing tide. In fragile cases, stress can crack the nucleus, leading to fragmentation events. Fragmentation is one of the dramatic possibilities at perihelion. As internal pressure builds, crust may break, releasing bursts of gas and splitting the body into smaller pieces. Such splits have been seen before in solar system comets. Shoemaker-Levy 9 broke into a train of fragments before colliding with Jupiter. If at last fractured, the fragments would continue on similar hyperbolic paths, and telescopes would track each one. Imagine a loaf of bread baking too fast in the oven, steam pockets swell, crust cracks, and pieces separate. Comets act in much the same way, only at a colder scale, with solar heat driving pockets of gas outward. Some cracks reseal, others widen, releasing fans of dust and jets that tilt the coma suddenly. If a full break occurs, it offers a cross-section, revealing inner material untouched for billions of years. Safety remains assured even in that case, because all paths stay far from Earth. A breakup would be a scientific gift, not a hazard, offering more fragments to analyze. Brightness may spike if fresh surfaces vent strongly, giving telescopes a brief bonus in data. Such moments are rare, but perihelion is when they are most likely to occur. Gas chemistry also changes under stronger heating. Carbon dioxide may fade in proportion as water dominates, or it may remain stubbornly high. If carbon dioxide stays strong, that proves the surface and near subsurface are layered differently than in most solar system comets. If water rises sharply, then the comet's core resembles ours more closely than we thought. Spectra split light into fine bands, each band carrying a signature of a molecule. From these, astronomers count how much gas escapes each second, a measure called the production rate. Rates for water, carbon dioxide, and carbon monoxide are benchmarks of activity, telling us how icy bodies store and release volatiles. At-last's rates will soon fill scientific tables, compared against Borisov and our own comets. Dust tails also grow more distinct at perihelion. Small grains stretch farther, painting long filaments across the starfield. Large grains stay closer, thickening the base of the tail and giving it a brighter head. By comparing these shapes to models, astronomers extract a distribution of grain sizes. Synchrone and syndine curves are mathematical tools for this. They trace where grains of certain ages and sizes should lie under solar radiation pressure. By overlaying such curves on images, one can see whether the tail matches predictions. If not, the dust may have unusual properties, porous or dense, light or dark, affecting how sunlight pushes them. Color changes may also appear. Some comets glow green when certain molecules like diatomic carbon are excited by sunlight. If Attalast shows this green tint, it means its chemistry includes those active molecules. Color is a simple but powerful clue, easily seen even in small telescopes. Comparison to Borisov becomes sharper here. Borisov's coma was dominated by water and carbon monoxide, a familiar pattern. Atlas instead shows strong carbon dioxide, a distinctive tilt. This difference underscores the diversity of nurseries in which such bodies form. Oumuamua remains the contrast, with no coma, no chemistry, only indirect inference. It is the quiet outlier, a fragment without plume or tail, perhaps baked or stripped before arrival. At-last, by contrast, is alive with activity, jets carving fans, dust writing lines, gases streaming visibly. The spectrum of interstellar objects now spans from silent shards to classical comets to chemically unusual hybrids. Think again of the freezer shelf metaphor. Different shelves produce different recipes of ice. At last is the shelf where carbon dioxide is common. Borisov, the shelf where water was plentiful. Oumuamua, perhaps no shelf at all but a splinter of rock. Each represents a region of a protoplanetary disk, frozen into matter, then flung into interstellar space. Together, they are samples of kitchens we cannot visit, but which send their recipes drifting through the galaxy. Jets not only vent gas, but carry momentum, pushing the nucleus gently. This causes small deviations in the orbit, detectable after weeks of careful measurements. Non-gravitational terms A1, A2, and A3 describe these subtle pushes mathematically. Though small, they must be included to keep the path accurate, especially for a body leaving forever. Rotation period combined with jet torque also affects long-term survival. If the torque spins the comet faster, centrifugal stress can crack the nucleus. If torque slows the spin, sunlight distribution shifts, changing activity zones. Either way, spin evolution is a key part of perihelion studies. Safety continues to reassure, with Earth distant and unthreatened, so observers can focus fully on learning rather than worry. The only risk is missing data if weather or geometry block observations. To counter this, networks of telescopes pass the watch across longitudes. Telescopes worldwide cooperate, each handing the baton to the next. Space-based instruments like Hubble or Webb add their precision, free from atmosphere. Spectrometers resolve faint lines, polarimeters catch subtle light twists, imagers map tail structure. Together they make a mosaic, a full picture from many instruments. Patience is again required. Perihelion lasts only weeks, yet analysis takes months as raw frames are calibrated and spectra modeled. Students and postdocs spend long hours reducing data, subtracting sky, correcting for noise. The reward is a plot that may look simple but represents hundreds of careful decisions. Imagine the nucleus itself at perihelion, a dark, irregular body a kilometer across, crust fractured, jets spraying sunward. The coma is a halo of dust, sunlight scattering off grains so faintly that a roomful of them would barely fog your air. The tail streams away for millions of miles, yet contains less mass than a handful of soil. Scale in comets is deceptive, vast in reach but slight in substance. Heat is both the sculptor and the destroyer. It sculpts by lifting gases and dust into a plume, revealing composition. It destroys by cracking crust and stressing the interior. Balance between those effects decides whether a comet survives its passage. Fragmentation remains uncertain. If the nucleus is strong, it will hold together, venting steadily. If weak, it may split, leaving a trail of small companions. Astronomers will be ready for either outcome, logging data whichever way it goes. Science thrives on both continuity and surprise. Continuity comes from measuring the same patterns, jets, ratios, brightness curves. Surprise comes from sudden outbursts or unexpected chemistry. At last may provide both, and both are equally valuable. Future missions may target the next interstellar visitor at perihelion directly. For now, we practice with at last, learning to interpret coma signals more finely. Each case makes us better prepared for the next, so no observation is wasted. Even a faint plot can hold a major lesson. Patience is rewarded not only by data, but by perspective. These objects cross once in a lifetime, yet their messages are timeless. Each carries a piece of another star's past, chemistry frozen for billions of years. By reading that piece, we expand our sense of what planetary systems can be. Now, perihelion is near, and the comet is at its peak. Water joins carbon dioxide, dust streams outward, jets flicker across the coma. The nucleus may crack, or it may endure, but either way its message is written in light. We watch, measure, record, and know this moment will not come again. Let's drift gently into another corner, carrying the image of perihelion's heat and the fragile nucleus enduring it. The story of Atlas is not finished, for outbound changes still await. Next, we will follow the fading coma as it recedes, comparing inbound and outbound, symmetry and asymmetry. And from those differences, we will learn whether the comet's layers are shallow or deep, uniform or fractured. Outbound is the next stage of the comet's life with us, the slow drift away from perihelion, carrying heat fading step by step. As distance increases, sunlight weakens and the gas flow that once roared begins to quiet into threads. The The coma shrinks, tails grow fainter, and the comet slides back into the dark where telescopes strain to keep it in view. But this fading stage is more than an afterthought. It is a mirror, a way to see whether inbound and outbound stories match. Symmetry is the concept astronomers hold here. If activity inbound was matched outbound, the comet's layers are likely uniform, with no surprises hidden deeper. If outbound activity lingers or shifts, it may reveal asymmetry in crust thickness or thermal conductivity. Such asymmetry is common, for comets carry fractures, slopes, and varying porosity across their surfaces. Heat penetrates only shallow depths each day, measured in centimeters rather than meters. That shallow skin depth means that some layers do not respond until days or weeks after closest approach. So outbound, a delayed release of gases can linger, giving the comet a second wind long after the peak of sunlight. By watching carefully, we trace the memory of heat as it migrates slowly inward. Think of a stone warmed by afternoon sun. Even after the lamp sets, the stone stays warm into the night. In the same way, a comet's crust stores heat, releasing it later, even as the solar flux weakens. That storage produces delayed jets, faint but persistent, writing asymmetries into the outbound coma. This makes outbound measurements as valuable as inbound, even though brightness is lower. Gas production rates are one of the first metrics to decline. Carbon dioxide, once vigorous, may fade quickly as its surface pockets empty. Water lingers longer because deeper reservoirs keep releasing vapor despite weaker sunlight. The changing ratio of gases outbound writes a second signature, distinct from the inbound phase. Dust also behaves differently outbound. Smaller grains already carried far down the tail do not return, but larger clumps near the nucleus may continue to drift outward slowly. This makes the outbound tail appear heavier at its base, with less fine structure at distance. By comparing images inbound and outbound, astronomers see whether dust release is steady or skewed. Polarization curves can also shift. As the coma thins, scattered light from dust grows easier to measure, less drowned by glare. If the polarization branch outbound differs, it may mean that fresh grains were exposed late, or that grain size distribution changed. This creates another layer of comparison between inbound and outbound dust properties. Rotation continues to modulate brightness, but the clock may change slightly. Jet torque near perihelion can accelerate or decelerate the spin, altering the rhythm. By measuring carefully, astronomers test whether the rotation period outbound matches the inbound curve. Even a change of minutes over weeks is evidence of torque from uneven jets. Stress on the nucleus may remain even as gases fade. If perihelion opened deep fractures, those cracks can keep venting outbound. Some comets even shed fragments after perihelion, not before, because delayed heating weakens them later. At-last will be monitored closely for any such surprises in the months after its closest pass. Safety remains the same, with wide distances keeping Earth secure. No matter how long activity lingers, the path remains hyperbolic, carrying the body outward forever. We will never see at-last return, so every measurement outbound is the last we will ever have. That finality gives a special weight to even faint data gathered months later. Color can also change outbound. In some comets, green glows from diatomic carbon fade quickly as production slows, leaving a whiter coma. If at-last's tint fades faster or slower than expected, it will hint at how carbon compounds are layered. Even subtle changes in coma hue are meaningful signals when recorded carefully across time. Comparisons extend again here. Borisov remained active outbound, fading smoothly but with no unusual asymmetry. Oumuamua showed nothing at all, silent both inbound and outbound, no coma to compare. If Atlas shows lingering carbon dioxide or delayed water jets, it becomes distinct again, a third variation. Think of a candle wick glowing even after flame is blown out. The ember lasts longer than expected. Outbound comets are those glowing embers, still venting faint gases after the main blaze is past. Such embers are precious to astronomers because they extend the dataset, giving longer arcs of activity. Atlas's outbound ember will be tracked as long as telescopes can see it. Dust tails stretch differently outbound. Radiation pressure continues to push grains away, but at weaker force, so the geometry shifts. The tail may appear straighter, less curved, with smaller angular spread. Modeling those changes provides constraints on grain size distributions and velocities. Gas lifetimes in space also matter. Certain molecules break down under sunlight quickly, others persist longer. Outbound, production slows while destruction continues, changing the balance of visible lines. From this, astronomers infer how surface composition evolves as the nucleus cools. Heat waves traveling inward may uncover fresh ices days after perihelion. Such delayed vents can appear suddenly, surprising observers who thought activity should be falling. These vents may create short bursts of brightness, giving the comet a second flare outbound. In this way, comets can fool predictions, forcing updates to thermal models. Stress fractures are visible in coma asymmetry. If one side vents longer, the coma appears tilted outbound. Such tilts may not match inbound tilts, because new cracks may have opened. Tracking the shift reveals whether perihelion permanently altered the surface. Rotation plus delayed heating may cause new phenomena. If jets torque the body enough, rotation period may shift noticeably. An accelerating spin can raise centrifugal forces, risking eventual fragmentation even outbound. Though rare, such cases are watched closely because they reveal mechanical limits of cometary strength. Observations will continue until the comet fades beyond reach. Large telescopes in Chile, Hawaii, and space will stretch their limits to keep the object in view. Each spectrum will be noisier, each measurement harder, but even faint detections carry value. The outbound arc is a final gift, filling in the closing pages of the biography. Science thrives on closure, and outbound phases provide that. Without them, we would only know half the cycle. With them, we see whether activity is balanced, delayed, or skewed. This knowledge sharpens thermal and compositional models for all comets. Imagine the nucleus now, drifting farther each day. The coma thins, jets weaken, tail fades, but the core still turns silently. It carries scars from perihelion, fractures etched into crust, altered spin, perhaps. These scars will travel outward for eons, unseen again by any eye on Earth. Memory of the comet will live only in data. Plots of gas rates, dust polarization, rotation periods, and tail geometry will remain in papers. Students decades from now will still cite Atlas, comparing new interstellar objects against it. In this way, outbound lessons become permanent threads in science. Comparison with local comets teaches us that asymmetry is normal. Many solar system comets vent longer outbound than inbound, storing heat in deeper layers. If Atlas behaves the same, it may be less exotic than its early chemistry suggested. If it behaves differently, it adds to diversity, proving that interstellar bodies carry more variety than expected. Dust properties may shift outbound because large grains dominate as smaller ones disperse. This creates a heavier look to the coma near the head. Polarization curves may flatten, showing more compact scattering from coarser particles. Such evolution tells us how ejection sorts particles over time. Water vapor outbound will also be a marker. If it persists longer than carbon dioxide, the thermal gradient inside the comet must be deep. If it fades too quickly, perhaps water was only thinly layered, while carbon dioxide filled the bulk. Either outcome is a clue, feeding into models of disk chemistry at birth. Patience will again be needed. Outbound signals are faint, but each line matters. Polarimeters, spectrographs, and imagers will stretch to their limits. The faint tail becomes a challenge for those who persist. Future missions may learn from this. If outbound monitoring is so valuable, space missions might be designed to linger longer. Instead of brief snapshots, extended arcs of observation will capture delayed effects. Such arcs turn fleeting visitors into long-term teachers. Philosophy, too, emerges here. Every fading comet is a metaphor for memory. Bright once, then gone, but leaving traces. The traces are not only in data, but in our sense of belonging to a wider universe. Each visitor reminds us that we are not isolated, but part of a galactic traffic. Now, at last, drifts outward, slower in brightness, but steady in message. Its carbon dioxide remains a marker, its dust still scattering, its water joining late. Even as it fades, each photon it sends tells a piece of its biography, and we are still listening until the last trace is gone from our sky. Population is the wider frame we now turn toward, because a single object is a story, but three together become a hint of statistics. In the past, astronomers believed interstellar visitors were rare guests, perhaps 1 in a million years bright enough to see. But the discovery of Oumuamua in 2017, Borisov in 2019, and Atlas in 2025 forced a new calculation. 3 arrivals in less than 10 years cannot be chance alone. It means our galaxy is filled with more wanderers than we had imagined. Numbers here are drawn from detection rates. A survey with wide-field telescopes scans the sky every night, and the number of detections per decade translates into a density estimate. If 3 have been found in under 10 years, then the true count of faint, unseen visitors must be vast. Some models suggest billions of such objects may be crossing the Milky Way at any given time. Think of it like raindrops on a street lamp at night. You only see the brightest ones, but the dark is full of others. In the same way, telescopes only catch the brighter comets and fragments that pass close enough. Most drift unseen, small or faint, sliding through the outer solar system without a trace. Yet the few we detect reveal the enormous background that must exist. Density estimates vary, but are striking. Some calculations suggest there may be 1 interstellar object larger than 100 meters for every cubic astronomical unit of space. That means the solar system is constantly crossed by such travelers, even if we notice only the brightest fraction. If that estimate is right, then trillions exist across the Milky Way, each a frozen record of a system's early chaos. This abundance changes how we picture the galaxy, not as empty, but seeded with countless fragments. Origin of this population lies in planet formation itself. When young systems form, giant planets scatter material relentlessly, ejecting most small bodies into interstellar space. Only a fraction stays bound to the home star as comets or asteroids. The rest become nomads, wandering between stars, silent until they pass close enough for us to see. Thus, every planetary system contributes to the interstellar traffic that drifts through the galaxy. Ejection happens through gravitational slingshots. A small, icy body strays near a giant planet, gains energy, and is flung outward beyond escape speed. Over billions of years, such encounters eject far more mass than is ever kept. This is why interstellar space must be crowded with ejected debris, even if most pieces are dark and tiny. Each one is a postcard from another nursery, a sample flung outward by cosmic billiards. Calculations suggest that our own system may have ejected 100 times more small bodies than it retained. If we look outward, every other star must have done the same, filling the galaxy with fragments. This is why the discovery of 3 visitors so quickly feels natural once detection methods improve. It is the same logic as fishing with a finer net. The fish were always there, but now they are caught. Technology plays a major role in this rising detection rate. Surveys like Pan-STARRS and Atlas scan vast fields, catching moving points by software rather than by eye. Future projects like the Rubin Observatory's Legacy Survey will deepen that reach, spotting smaller, fainter visitors. When that survey begins full operation, we may find multiple interstellar bodies each year. This will transform the sample from anecdote into genuine statistics. Frequency of detection then becomes meaningful. If one arrives every year or two, we can expect to compare dozens within a generation. That means we will begin to map diversity the way we have mapped exoplanets. We will see whether carbon dioxide dominance like Atlas is rare, whether silent shards like Oumuamua are common, or whether Borisov's classical comet style is typical. Think of exoplanets again for context. In the 1990s, a handful of planets were known, odd giants close to their stars. Now thousands are catalogued, showing endless variety. So too with interstellar objects, from 3 to dozens, then to hundreds, each adding to the pattern. The more we find, the more we will understand what is normal and what is exceptional. Surveys also hint at size distribution. Large objects are rare but visible far away, while small ones are common but faint. Oumuamua, 100 meters or more, was just bright enough to detect. Borisov, slightly larger and actively venting, was easier to see. Atlas, perhaps a kilometer across, carries brightness through its coma and tail, making it a clearer target. Small objects, tens of meters across, may pass through unnoticed every year. They are too faint for current surveys unless they pass extremely close. Yet their abundance must be huge, given what we know about ejection processes. This means Earth's skies are crossed often by unseen messengers, silent and invisible except to future instruments. Distribution across the galaxy may also be uneven. Star-forming regions with many young giants eject more debris. Quiet systems with smaller planets eject less, leaving fewer wanderers. But across billions of stars, the total population becomes staggering. It is a quiet galactic ocean, with every star contributing fragments to the tide. Safety is worth considering in numbers too. Though countless pass near, the chance of collision with Earth is still extremely low. Most sweep by at vast distances, their energy carrying them swiftly outward. Only in extraordinary coincidence could one impact, and even then, sizes are usually small. So for humanity, this traffic is a spectacle, not a hazard. Science gains more than it risks from this abundance. Each detection allows chemistry to be sampled, dust to be analyzed, tails to be modeled. Comparisons grow sharper with each new entry in the ledger. Over decades, we may have enough data to outline the families of interstellar objects. Some will be dry, some wet, some exotic, each group telling a different origin story. Population also intersects with planetary science. The ratio of ice to rock, the dominance of carbon dioxide or water, the porosity of grains, all are clues about disk conditions. Each object becomes a proxy for the exoplanetary disks we cannot visit. By building statistics, we construct a comparative planetology of nurseries across the galaxy. This is why Atlas and its cousins matter beyond their brief appearance. Imagine a galaxy where every star contributes a halo of fragments. Around each star, an invisible cloud of ejected comets expands slowly into the galactic disk. The Milky Way becomes not empty, but filled with small, icy travelers drifting endlessly. Our solar system crosses these streams, catching the occasional guest. This perspective changes our sense of scale. The interstellar medium is not only gas and dust, but countless exiles. Future instruments will sharpen this census. Infrared telescopes in space may catch faint glows of visitors otherwise missed. Wide-field surveys on Earth will catch more bright passages. Together, they will yield real population curves, distributions of size, activity, and composition. From that, we will know how typical our solar system's debris is. 3 detections are not enough to define a population, but they are enough to break the old belief of rarity. Before 2017, the first was only a theory, assumed but never seen. Now, 3 stand in the record, each one unique, each one proof of abundance. The line from none to 3 is already a revolution in our sense of the galaxy. Think again of raindrops. At first you see one, then another, then a third, and you realize the air is full of them. So too here. 3 detections reveal the constant fall of interstellar fragments. We now know the Milky Way is alive with such motion, even if we see only the brightest few. Statistics give more than numbers, they give confidence. Confidence that diversity is not anecdote but pattern. Confidence that our models of disk ejection are accurate. Confidence that the next detection is not miracle but expectation. This shift is what makes population study so powerful. Philosophy follows behind the math. When we realize the galaxy is full of fragments, we sense that we are surrounded by evidence of other systems. Every visitor is proof that planets are common, that ejections are normal, that we are not alone in mechanism. The story of planetary birth is written not only in light from disks, but in solid bodies crossing the dark. This realization deepens our connection to the galactic whole. Now we can predict with better clarity. With new surveys, we expect interstellar detections to become almost routine. Each routine discovery will still be precious because each carries a unique signature. But the shock will fade, replaced by careful classification. That is how sciences mature, moving from surprise to taxonomy. Classification may one day divide interstellar objects into types. Type 1, silent shards like Oumuamua. Type 2, classical comets like Borisov. Type 3, CO2-rich hybrids like Atlas. More types may emerge, but already this framework begins. Future decades will see a catalogue grow. Each object will have a page of orbital elements, spectra, dust curves, rotation period. Together, these pages will form the first atlas of interstellar small bodies. Astronomers will leaf through that atlas, comparing one signature to another, just as we now do with exoplanets. The atlas will be a map of diversity, written in cometary light. Patience remains required, but the direction is clear. 3 detections have shifted the paradigm from rare to common. The galaxy is filled with these fragments, and now we know how to catch them. With each one, we learn more about formation zones, disk chemistry, dust properties. The story of 3L Atlas is one page, but many more are waiting to be added. Chemistry is the language written into every comet because the gases it releases are direct messengers of its birth environment. Each molecule carries a frozen memory of the place and time where it first condensed into ice. By splitting light into spectra, astronomers can read those memories billions of years after they formed. This is why interstellar visitors are so valuable. They are samples from systems we can never reach. Disks around young stars are the kitchens where such recipes are set. In these disks, temperature varies with distance, creating zones where different molecules freeze out into solids. Near the star, heat keeps water as vapor, but farther out, water can freeze, joining dust grains to form comets. Even farther, carbon dioxide and carbon monoxide can freeze onto grains, building layers in colder shelves. Think of it as a series of freezers in a kitchen. The inner one is warm, the outer one is cold, each holding different ingredients. A comet's ices are like a shopping list from whichever freezer shelf it was built. Water-rich comets formed in the midzone, CO2-rich comets formed further out, and Keough-rich bodies formed at the edge. By studying their gases, we learn what shelves were stocked in distant systems. Water is the most common ice in our own comets because most formed where water was abundant. Carbon dioxide plays a smaller but important role, contributing to early activity at colder distances. Carbon monoxide is even more volatile, requiring the coldest environments to freeze solid. Each of these is a thermometer, telling us what the temperature was in the birth zone. Atlas tells us something unusual already. Its strong CO2 signal suggests a colder nursery than most of our local comets. This makes it a bridge between familiar solar system chemistry and more exotic outer disk chemistry. It reminds us that every system may stock its shelves in slightly different ratios. Borisov, by contrast, showed a water-heavy balance, similar to comets here. That made it a reassuring sign that our recipes are not unique. Oumuamua showed almost nothing, its surface stripped or altered so much that chemistry could not be read. Together, they form a triangle of possibilities, showing the wide range of outcomes. Origin studies aim to connect these visitors to disk models. Young stars are often surrounded by swirling disks of gas and dust, glowing in infrared. We cannot sample them directly, but comets from them become traveling archives. When one enters our solar system, it is as if a page from a distant library has drifted to our desk. Analogy helps again here. If you walk through a market, each stall has a flavor, spices, fruits, grains, and together they form the culture of a town. Each comet is like a stall's sample, telling us what that kitchen once made. Atlas may be the stall of a colder market, where CO2 was abundant and stored generously. Disks are not static, but evolve over millions of years. At first, heat from the forming star pushes ices outward, moving the ice lines. Later, as gas thins, radiation from nearby stars can alter the chemistry balance. Comets preserve a frozen snapshot of whichever stage they locked their ices in. Thus, Atlas is not just a body, it is a frozen timestamp from its home disk. Porosity of dust is another clue about disks. Grains that are fluffy form when dust collides gently, sticking in low-energy environments. Compact grains form when collisions are harder, in more turbulent zones. Atlas's dust seems unusually porous, hinting that it grew in a calmer outer disk where collisions were soft. Gas ratios also reveal disk processing. High CO2 relative to water may mean the disk's mid-plane was cold enough for CO2 to freeze, but not warm enough to drive it away. Such conditions vary with star type, with cooler stars having closer ice lines. Thus, Atlast may have formed around a star not unlike our Sun, but with slightly colder chemistry. Think of a recipe adjusted for a different kitchen. The flour and sugar may be the same, but the spices change depending on what is stocked. Comets are these recipes, carrying variations based on what shelves were available. Some are heavy with water, some with CO2, some with carbon monoxide. The diversity is the story, and the galaxy is wide enough to allow endless recipes. Comparisons to exoplanetary disk observations strengthen this point. We have seen disks around young stars glowing in lines of CO and water vapor. From these we know where molecules survive and where they freeze. But direct samples are impossible, except when a comet like Atlast passes by. It is the only way to test disk chemistry with real material. Models of disk evolution use comets as benchmarks. If a disk predicts high CO2 ices in outer regions and Atlast matches that prediction, the model gains weight. If it diverges, models must adapt, showing that disks are more varied. Thus, each interstellar visitor becomes a test of theory, a small but precise experiment in galactic chemistry. Lessons also extend to planet formation itself. The same ices that form comets are the building blocks of planets. A planet's atmosphere and surface water come largely from these frozen grains. By measuring comets, we indirectly measure the inventory of raw materials for planets. This is why Atlast's CO2 dominance matters. It hints at planets richer in CO2 in its system of origin. Exoplanets may bear the results of these differences. Some may be water-rich, others CO2-rich, depending on which ices were delivered during formation. This diversity explains why exoplanet atmospheres we measure look so different from Earth's. Every interstellar comet that passes is a clue to why such variety exists among planets. Dust microphysics adds more depth. The size distribution of grains controls how light is scattered and how ices attach. Porous aggregates carry more surface area for ices. Compact grains carry less. Thus, a comet's dust is not trivial. It is a map of disk growth conditions. Atlast's dust is one more data point in this map. Volatiles like methane, ammonia, or organics may also appear in spectra. If detected, they would hint at chemistry rich in complex molecules. Such molecules are precursors to life, suggesting that disks can stock far more than water and CO2. Atlast may or may not show these, but even a lack is informative. Absence tells us what its nursery did not supply. Philosophy lingers here too. Each comet is a frozen letter mailed across space, carrying the accent of its home system. We are not reading myths, but the actual script of chemistry carved into ice. This is how astronomy becomes intimate, not just looking, but touching the kitchens of distant stars through their fragments. It is slow reading, but every line is real. Now, imagine the galaxy as a library of kitchens. Each star forms a disk, each disk ejects debris, each debris carries a sample. Over time, these samples drift into interstellar space, waiting to be found. Our telescopes are the librarians, cataloguing each book as it passes through. Atlast is one such book, its pages written in CO2 lines and dust curves. Disks around stars evolve with turbulence and radiation. Stars more massive than the Sun blast stronger winds, shifting ice lines farther outward. Cooler stars keep ices close, building comets richer in certain volatiles. Thus, the chemistry of comets across the galaxy must be wildly diverse. At last is one word in that dictionary, a single but distinct entry. Think of language analogies. Every human language uses sound, but each has unique words. So too, every disk makes comets, but each has unique ratios of water, CO2, CO. Atlast's accent is CO2, Borisov's was water, Oumuamua's silence was absence. Together they form the beginning of a galactic dialect. Future surveys may find dozens more. Each one will add a new page, a new balance of volatiles, a new dust curve. By comparing, we will begin to write the first grammar of interstellar bodies. From that grammar, we can infer how systems vary, how common Earth-like recipes are, how rare exotic ones. This is how interstellar fragments tie to exoplanet science. Exoplanets themselves are hard to study directly. We glimpse their atmospheres in faint transits, a sliver of starlight filtered through gas. But interstellar comets are physical fragments, offering solid evidence of disk chemistry. Together, planets and comets are complementary. One shows the end result, the other shows the ingredients. That complementarity is a profound connection. Now, the outbound arc of Atlast becomes even more important. Its lingering activity lets us keep sampling its chemistry, testing how ratios evolve with distance. The fading coma may reveal weaker lines of carbon monoxide or even faint organics. Each additional detection refines the frozen story of its birthplace. The longer we watch, the more complete the translation becomes. Patience is our method. Weeks of spectra accumulate into a clear picture. One line alone says little, but dozens across time say much. This patience is the hallmark of astronomy, and comets reward it. For Atlast, the reward is a deeper look into another disk's inventory. Motion is not only about orbits across the sky, it is also about the hidden turning of the comet itself, the slow spin of its nucleus. Every comet is a rotating body, shaped irregularly, carrying mass unevenly, and therefore responding to sunlight and jets in complex ways. For at last, the exact period of rotation remains to be pinned down, but hints can already be seen in the flickers of its light curve. These flickers come from patches of brightness shifting as the nucleus turns, or from jets modulating activity as they sweep in and out of sunlight. Rotation is not fixed forever. Gas vents act like tiny thrusters, each one pushing unevenly, each one applying torque. Over days and weeks, these small pushes accumulate into changes in the spin. Some comets lengthen their period, others shorten, depending on which jets dominate. Think of a toy top set spinning on a table. As it slows, small nudges from the surface tilt its motion, making it wobble. In the same way, cometary rotation is sensitive to the tiniest nudge. A jet venting carbon dioxide from one crack can shift the rotation by fractions of a second per day. Over weeks, those fractions add up to noticeable changes, altering the comet's rhythm. Stress arises when spin changes too much. If the rotation speeds up, centrifugal forces pull outward, straining the crust. Fragile bodies with low cohesion cannot hold forever, and cracks spread across the nucleus. In some cases, the body splits into multiple fragments, leaving a train of smaller companions. Shoemaker Levy 9 is the classic reminder. It split into a string of fragments before colliding with Jupiter in 1994. That comet was torn by Jupiter's tidal grip. But the lesson applies. Comets are weak, and stresses reveal their limits. Atlast is not under tidal stress from planets, but internal torque from jets can still threaten it. If spin accelerates beyond the structural limit, breakage is possible. Material strength is modest for comets. Most nuclei are porous mixtures of dust and ice, more like loose snow than solid rock. Cohesion may be measured in kilopascals, far below that of solid stone. This is why comets fracture easily, shedding chunks even without strong impacts. Rotation period interacts with this weakness. Shorter periods mean higher outward pull at the surface. If the pull exceeds cohesion, the crust fails, releasing slabs or breaking the body apart. Some comets spin fast enough to risk this outcome, while others settle into stable rhythms. Analogy helps clarify. Think of a clay pot spinning on a wheel. If it spins too fast, soft walls stretch outward, threatening to tear. A comet nucleus is that fragile pot, and sunlight-driven jets are the hands pushing it faster. The outcome depends on balance. Steady jets keep spin stable. Unbalanced ones push the limits. At last is one more test of how long such a fragile pot can hold. Torque is described by simple physics but measured in subtle ways. Astronomers track small changes in brightness curves, timing rises and falls carefully. If the curve shifts, the rotation period has changed. From the shift, one can calculate the torque from jets and thus infer activity patterns. Jets themselves depend on surface cracks. Some open under heat, others close with shadow, each controlling when gas is released. If one vent dominates, torque is steady and predictable. If many vents compete, the torque becomes chaotic, spinning the comet unpredictably. Chaos in spin leads to tumbling. Instead of rotating on a single axis, the body can wobble, precessing like an unbalanced top. Such tumbling alters which areas see sunlight, changing jet activity further. The cycle feeds on itself, making the body's future spin hard to predict. Oumuamua may have tumbled this way, its brightness curved too irregular for simple rotation. This tumbling suggested complex torque histories, scars of past vents or collisions. At-last might do the same if outgassing is unbalanced, producing erratic patterns in light curves. Even small deviations are instructive because they show how fragile bodies respond to internal forces. Strength is tested at perihelion when heating is strongest. If At-last survives this passage intact, it will prove its cohesion is high enough for stability. If cracks widen, partial fragmentation may occur, creating smaller companions to study. Either way, science gains. Survival tells us one thing, fracture tells us another. Imagine the internal view of such a body. Pockets of ice lie beneath dust. Gas builds pressure as sunlight seeps in. Stress accumulates, seeking weak points until a fracture line forms. Jets erupt, pressure falls, but torque has already changed the spin. This cycle repeats, each vent altering the mechanical state of the nucleus. Non-gravitational forces are how these torques appear in orbits. Orbital fits include small parameters A1, A2, A3, describing tiny nudges from outgassing. For At-last, these terms will refine its escape path. Though small, they must be included for accurate long-term trajectories. Spin changes can also alter surface illumination. If orientation shifts, new areas face the sun, activating fresh vents. This cascades into further torque, continuing the feedback loop. Over time, the nucleus evolves not just chemically but mechanically, a changing machine in motion. Breakups are the most dramatic outcomes. If rotation grows too fast, centrifugal forces exceed strength and slabs fly outward. Sometimes the whole nucleus splits, leaving fragments on parallel tracks. Such breakups are tragic in one sense, but they expose new material never before seen. Dust from fragments adds to the coma, thickening it suddenly. Brightness spikes, tails flare, and astronomers rush to record the change. Polarization curves shift, reflecting fresh grain populations. Chemistry too can change as new ices are exposed to sunlight. Examples abound in solar system history. Comet Linear disintegrated in 2000, leaving a cloud of debris. Comet Lenin faded into fragments in 2011, losing its central core. These events remind us that comets are fragile and at last may face similar risks. The difference is that at last will not return, so every observation is final. Think, again, of fragile analogies. A snowball left under a lamp melts unevenly, dripping on one side, cracking on the other. A comet nucleus is that fragile snowball, only stretched to kilometer scales. Jets carve channels, torque twists the body, cracks spread. The snowball may survive the lamp or collapse into wet shards. Either way, it tells a story. Rotation also influences how dust spreads. Fast spins fling grains outward more easily, giving a broader coma. Slow spins release dust gently, letting grains settle close. Thus, the coma's shape is a mechanical fingerprint of the nucleus's spin. Stress mechanics matter for interstellar context too. If at last is typical, then most interstellar comets must endure similar torques. Some will survive long journeys, others may fracture en route, leaving smaller shards. This may explain why some visitors appear small and inactive, while others vent like classical comets. Models help translate mechanics into predictions. Computer simulations test how jets alter rotation, how fractures open, how fragments behave. These models match against real data from ATLAS, refining assumptions about strength. With each case, we build better predictive tools for future visitors. Safety again stays steady. Even if ATLAS breaks, the fragments follow hyperbolic paths, no threat to Earth. The real effect is on science, with more surfaces exposed, more clues to gather. Astronomers prepare for such events, scheduling time to capture surprises. Philosophy whispers behind the mechanics. Fragile bodies remind us of impermanence, of how easily structures crack. Yet in that cracking comes knowledge, the opening of hidden layers. What breaks is not lost, but revealed. So with comets, so with the universe, fragility can also be a teacher. Now at last continues through its outbound path. Torque from jets may still alter its rotation. Stress may linger, fractures may grow, even as sunlight fades. We cannot predict whether it will endure intact or split, only watch patiently. Patience is astronomy's way. Weeks of faint dots, spectra stacked, curves timed. From those dots we infer torque, from those curves we read spin. The nucleus remains unseen, but its mechanical life is known through careful inference. Let's drift into another corner of this journey, carrying the awareness that even in silence, a comet turns, strains, and endures. The mechanics are not separate from chemistry, but partners, each shaping the other. Next, we will turn toward the dust itself, how grains carry signatures of birth, how they evolve in flight, and how light scattering reveals their secrets. From that dust, we will learn the fine textures of another world's nursery preserved across space and time. Dust is the second voice of every comet, quieter than gas but longer lasting and often more revealing. While gases vanish quickly into sunlight, dust grains stay behind, scattering light and drifting for millions of kilometers. For ATLAS, dust is not only a tracer of present activity, but also a preserved memory of its nursery. Grains lifted now were once locked together in a protoplanetary disk around another star. Size is the first key property astronomers measure. Small grains scatter light efficiently, producing a soft halo. Larger grains scatter less and drift slowly, forming the denser base of a tail. By comparing coma brightness in different colors, we infer the distribution of grain sizes. Think of flour, sugar, and pebbles tossed into the air. Flour makes a haze, sugar sparkles, pebbles fall quickly. Comets release the same mix of fine and coarse grains. In Atlast, the balance of fine versus coarse dust tells us about cohesion in its crust and the energy of its jets. Gentle jets lift mostly flour, stronger jets lift sugar and pebbles as well. Polarization is the deeper tool. When sunlight bounces off grains, it twists the plane of light in subtle ways. By measuring polarization at different angles, astronomers read the texture of dust. Atlast shows an unusually deep negative branch in polarization, unlike many of our comets. Negative branches mean grains are porous, fluffy aggregates of smaller particles loosely bound. Compact grains give weaker signals, porous grains give strong dips. This tells us that Atlast's dust is likely pristine, preserved without heavy processing by heat. Such porosity is a fingerprint of an outer disk origin where collisions were gentle. Analogy again clarifies. Imagine dry snow compared with wet snow. Dry flakes are fluffy and scatter light widely. Wet snow is dense and reflective. Atlast's grains are like dry snow, fragile and porous, easy for gas to lift. That fragility suggests a world where sunlight never hardened the surface. Distribution of dust sizes can also reveal hidden layers. If perihelion released larger grains, while outbound tails show finer ones, the sequence reflects depth. Perhaps deeper ices carried coarser grains, locked tighter until stronger heat freed them. Watching this sequence gives us a slow-motion cross-section of the nucleus. Dust tails themselves are laboratories. Radiation pressure pushes small grains harder, bending the tail into elegant arcs. Larger grains lag closer to the nucleus, thickening the near head. By fitting synchrones and syndines, astronomers decode the ages and sizes of released grains. Synchrone curves mark when grains were released, syndine curves mark their size. Overlaying these on images lets us trace back to the moment of ejection. Thus, a photograph of a tail is really a timeline, each filament a record of a specific burst. For Atlast, this timeline is being drawn night by night, arc by arc. Color of dust is another clue. Blue scattering means smaller grains, redder tints mean larger or darker particles. Atlast's coma will be studied across wavelengths to map this color shift. From that, astronomers infer the mineral and organic content of its grains. Organics may darken dust, giving comets a reddish hue. Porous grains coated with organics scatter light differently from pure ices. If Atlast's dust shows this redness, it hints at a nursery rich in complex molecules. If it remains neutral, it may have formed in a colder, simpler zone. Texture matters as much as composition. Fluffy aggregates trap sunlight differently than compact grains. They also sublimate differently, releasing ices more easily. Thus, polarization and color together give a portrait of texture plus chemistry. Think of dust as a diary written in grains. Each grain is a word, each scattering curve a sentence. Together they compose a chapter about the environment where they grew. For Atlast, this chapter is different from Borisov's and silent where Oumuamua's dust was absent. Comparison again sharpens meaning. Borisov showed pristine but classical dust, reassuringly similar to our comets. Atlast shows more porous grains, deeper polarization, pointing to differences in processing. Oumuamua showed no dust at all, remaining mute in this voice. Thus, 3 visitors give us 3 distinct entries in the dust dictionary. Porosity also ties to disk physics. Porous grains form in calm midplanes, where gentle collisions let aggregates stick. Turbulent disks produce more compact grains ground down by harder hits. At last's grains therefore whisper of a calm birthplace far from violent inner zones. That birthplace is recorded not in ice, but in the fragile structure of dust. Rotation interacts with dust too. Fast spin flings grains outward more forcefully. Slow spin lets grains hover close, thickening the coma. Thus, the dust halo reflects both internal mechanics and external light pressure. Stress fractures also affect dust release. When cracks open, fresh vents lift clumps of material. These clumps can fragment in flight, seeding the coma with unusual patterns. Such events appear as bright knots or arcs in tail images. Examples in solar system comets are instructive. Comet Hale-Bopp showed dramatic dust arcs in the 1990s, tied to rotation cycles. Comet 67P, studied by Rosetta, revealed porous grains clumping in jets, then dispersing into the coma. At last may echo these behaviors, but with chemistry not seen before. Dust also carries organics important for astrobiology. Laboratory analysis of comet grains from stardust showed complex molecules. If Atlas shares such grains, it means its nursery was chemically rich, not sterile. Even if we cannot sample them directly, polarization hints at whether organics coat the grains. Light curves also test grain size. If brightness fluctuates quickly, small grains dominate, carried easily by jets. If brightness fades smoothly, larger grains hold sway, slower to leave. Thus, photometry becomes a dust thermometer, indirect but reliable. Porous grains have further implications. They darken faster under radiation, changing albedo over time. They also fragment more easily, producing secondary tails of smaller debris. So observing them outbound is critical, catching late-stage disintegration. Imagine the path of a single grain. Lifted by a jet, carried into sunlight, pushed outward by radiation, it drifts into the tail. Along the way, it polarizes light, reflects colors, carries a chemical skin. That single grain is a messenger, silent but precise, carrying a signature of its home. Philosophy emerges even here. Each grain is insignificant by itself, yet together they build a visible halo. Each scattering pattern is subtle, yet together they reveal deep truths about formation. Dust is humility and power in one, reminding us that large stories can be told by the smallest parts. So it is with comets, so it is with cosmos. Now, at last, continues to vent, dust rising in slow plumes. Polarimeters record curves, spectrographs trace faint colors, imagers map arcs. Each tool adds a line to the dust chapter, and when combined, they reveal the fine texture of another system's nursery. Meaning is not always written in equations, but in the way discoveries reshape our place in the cosmos. When Oumuamua first appeared, it forced us to see the galaxy differently, not as empty, but filled with silent fragments drifting past. When Borisov followed, it showed that other systems send comets much like our own, linking us to a wider family. Now with Atlas, we are reminded that diversity is the true rule, not uniformity, and that our solar system is not the template for all. Philosophy in astronomy grows naturally from such realizations. Every visitor tells us we are part of a galactic traffic, streams of debris flowing between stars. We are not isolated, not alone in our processes. but joined by the constant exchange of matter across space. This exchange is subtle, silent, but it binds us into a greater community. Think of a city with countless households, each discarding scraps that drift into the street. Those scraps are not the whole of the home, but they carry hints of its flavor. So too, comets like Atlas are scraps from nurseries, drifting into the shared road of space. From them, we infer not the full home, but its recipes, its conditions, its early seasons. Time itself is another teacher here. These fragments may have wandered for millions or billions of years. Each orbit around its parent star ended long ago, replaced by exile into interstellar dark. Yet even after such exile, they still carry intact the ices and grains of their birthplace. That endurance reminds us that memory is possible even across cosmic ages. Fragility is part of the message too. Comets fracture, jets twist them, sunlight erodes them, yet they persist long enough to reach us. They are weak in strength but strong in journey, carrying chemistry faithfully. In that sense, they mirror human life, fragile in body, enduring in story. Astronomy becomes not only study but a mirror, reflecting lessons about our own place. Connection is what many listeners seek in these narratives. Science describes jets and spectra, but beneath it lies the human need for belonging. To know that fragments drift between stars is to know that systems are not sealed off, but linked. Each link is a quiet reminder that we too live inside a web of galactic relations. Belonging has always been part of astronomy. Ancient people traced constellations to map their place in the sky. Now we trace interstellar comets to map our place in the galaxy. The shift is vast, but the motive is the same: to feel at home in the larger whole. Atlas adds a new symbol to that sense of home, a sign that the road is busy. Imagine standing at a shoreline watching driftwood float by. Each piece comes from some distant forest carried by currents you cannot see. You may never know the exact tree or storm, but you know the world is wide and connected. Interstellar comets are our driftwood, carried by invisible galactic currents into our harbor. They remind us that the Milky Way is not a static place, but a living sea. Diversity is another quiet truth. Oumuamua, Borisov, Atlas. 3 visitors, 3 faces, none like the other. This is not noise, but the true pattern that nature makes many outcomes. Our solar system is one version, not the version, and humility is the proper response. Diversity means there are likely countless types we have yet to see. Humility is a gift astronomy returns often. It tells us that we are small, fragile, brief, and yet part of something vast. To meet travelers from other stars is to be reminded of scale beyond imagination. They show us that even when we think we know what comets are, there is always more. Humility is not defeat, but an opening, a way to learn without assumption. Fragile bodies also echo impermanence. They appear suddenly, blaze briefly, fade into darkness, never to return. This is the fate of comets and of many moments in life. Yet their brevity does not lessen their value. It sharpens it, making every observation a treasure. So too with human experience, transient but meaningful because of its fragility. Now consider the psychology of watching such visitors. An astronomer spends nights gathering photons from a faint smudge. Each photon has traveled across kilometers of space, carrying a bit of information. The observer sits under cold air, recording patiently, knowing this is the only chance. That patience is both science and meditation, a lesson in attention. Attention itself is a theme worth noting. Comets train us to notice faint things, to value subtlety, to listen for whispers. At last is not bright to the eye, not dramatic to the crowd, yet it teaches volumes. In that sense, astronomy becomes a discipline of care, of paying close attention to the quiet. And in the quiet, meaning appears, not forced, but revealed slowly like a dawn. Think of how easily noise drowns meaning in daily life. We rush past details, missing the small signs that matter. Astronomy asks us to slow, to notice a faint moving point, to let significance unfold in time. At last is such a point, humble in brightness but immense in meaning. It shows that sometimes the smallest signals are the ones that change perspective most. Perspective itself is reshaped by these visitors. We once thought interstellar space empty, now we know it is seeded with fragments. We once thought comets were only local, now we see they belong to every star. We once assumed our solar system was the template. Now we learn it is one of many recipes. Each new perspective widens the frame in which we place ourselves. Memory is another thread. At last will fade, but its spectra, curves, and images will remain in archives. Future students will scroll through data tables, reading numbers that trace its path. To them it may be history, but the meaning will still be alive. A reminder of diversity, of galactic motion. So comets give not only science, but a long memory for culture. Culture has always responded to astronomy. From myths of shooting stars to calendars set by lunar phases, the sky shapes human meaning. Now interstellar comets may enter our literature, symbols of chance meetings, of journeys across darkness. They may represent impermanence, or connection, or exile, depending on the storyteller. Science gathers the facts, but culture gives them wider life. Exile is perhaps the most poetic theme here. Each interstellar comet was once part of a home, circling a star before it was thrown out. Now it drifts without return, crossing starfields silently, an eternal wanderer. We recognize in that exile something familiar, the feeling of dislocation, of searching for place. Yet exile does not erase value, it spreads it, carrying chemistry to new worlds. Worlds may even be seeded by such fragments. Some theories propose that organics and ices travel between systems on comets. If so, at last is not just a visitor, but a courier, a piece of the galaxy's long biochemical exchange. Perhaps life itself gains from such wandering carriers, spreading potential across space. This idea blurs the boundary between science and myth, but both point toward connection. Connection returns again and again. Astronomy is less about isolation than about links, threads binding us to stars and dust. At last is one such thread, temporary but vivid. To watch it is to feel stitched into a wider tapestry, woven not only by starlight but by moving bodies. The tapestry is not static, it grows as each visitor is noticed, each thread added. Now philosophy must meet patience again. The comet will fade, new ones will come, but the larger meaning is cumulative. Each detection is a sentence. Together they form a galactic story. That story is one of diversity, fragility, exile, and connection. It is also one of endurance, of fragments carrying chemistry across ages. Endurance may be the deepest theme of all. These bodies travel for millions of years, unlit, unseen, yet intact. They endure cold, radiation, darkness, until at last they pass near a star. In that moment they flare briefly, a candle in night, and then are gone. That endurance gives weight to their fragility, reminding us that strength and weakness coexist in every form. Imagine a traveler crossing continents on foot, carrying only scraps of memory. By the time they arrive at your door, their clothes are worn, their steps are slow, yet their message is intact. So too, at last arrives weary but whole, carrying ices from its nursery across interstellar distance. We welcome it briefly, record its message, and watch it leave again into the dark road. It will not return, but its message stays in our shared memory. Philosophy of astronomy is simple yet profound, to know that we are part of something larger. Comets like at last give that knowledge in concrete form, small but undeniable. They do not argue or persuade, they simply appear, and by appearing they teach. They teach humility, patience, attention, connection, impermanence, and endurance. Each of these lessons is as real as any spectrum. Now, the human meaning is clear. We live in a galaxy not empty but full, not quiet but whispering, not still but in motion. Every visitor is a whisper made visible, a faint voice of another star. To hear that voice is to realize we are neighbors in a cosmic community. We are not alone, not by process, not by chemistry, not by destiny. Exploration has always been the next step in astronomy. We look, then we reach. Telescopes gave us spectra of comets, but spacecraft gave us Rosetta's close images and Stardust's returned grains. The same leap is now imagined for interstellar visitors, bodies that pass once and never return. To meet them directly would be to touch another star's chemistry with our own hands. Missions to such targets face challenges unlike any local comet. The first is speed, because interstellar bodies sweep through the solar system at tens of kilometers per second. By the time one is detected, it is often already inbound, leaving little time to plan. This urgency demands faster spacecraft and earlier warning systems. Think of trying to catch a train running past the station. You must sprint before it arrives, not after. With comets like at last, detection may give months of notice, but building a spacecraft takes years. Thus we need pre-built probes, waiting like arrows in a quiver. When the next visitor appears, the arrow must already be ready to fly. Concepts for such missions already exist. One is the Comet Interceptor by ESA, designed as a spacecraft on standby at the L2 point. It will wait in dormant mode until a target appears, then depart quickly to meet it. Although designed for solar system comets, its method could be adapted to interstellar bodies. Speed is the hardest requirement. Chemical rockets cannot reach the velocities needed for most intercepts. Advanced propulsion like solar sails, ion engines, or even nuclear systems are often discussed as solutions. The dream is a probe that can accelerate fast enough to catch up within a few months. Trajectory design is another barrier. Visitors come from random angles, often steep to the plane of the solar system. Matching that trajectory requires large velocity changes, more than most spacecraft can provide. Engineers model slingshots around planets or even the sun itself, maneuvers that give boosts. Such slingshots could fling a probe outward at interstellar speeds. Think of a stone slung by a sling. The faster you spin, the harder it flies. Planetary gravity assists are cosmic slings, giving probes momentum from Jupiter or Earth. But timing is critical, and an interstellar visitor's sudden arrival rarely matches planetary alignments. Thus, prepositioned spacecraft may be the only reliable answer. Technology is advancing in this direction. Solar sails are being tested as lightweight propulsion, pushed by photons with no fuel. Over long distances, sails can build immense speed, enough to catch even fast bodies. Ion drives too offer efficient continuous thrust, though they require power and patience. These methods may one day turn intercepts from dream to reality. Sample return is the boldest vision. Imagine scooping dust from an interstellar comet and bringing it back to Earth. That dust would be chemistry from another nursery, tested in our labs with every instrument. It would be the first solid matter from another star system in human hands. Such a mission would rival Apollo or Voyager in symbolic weight. Challenges are immense. Dust moves at relative speeds of tens of kilometers per second, too fast for gentle capture. Stardust solved this by using aerogel to slow particles without destroying them. The same technique could be adapted for interstellar dust, though impacts would be even harsher. Careful design is needed to gather without obliterating the sample. Now imagine the science return. One grain from at last could tell us about ices and organics billions of years old. Isotopic ratios would reveal details of its parent system's chemistry, things spectra cannot show. Complex molecules could be tested for prebiotic potential, hints of life's building blocks. It would be a direct handshake with another world. Partnerships may be key. Such missions are too costly for one agency alone. International cooperation, pooling resources from NASA, ESA, JAXA, and others is the path. Together, humanity could share in the glory of touching another system's fragment. This global reach echoes the global nature of the sky. No one nation owns the stars. Think of Voyager again, still moving outward with its golden record. That mission was built with 1970s tools, yet it endures. Imagine what modern technology, guided by decades of learning, could build for an interstellar probe. It would be both an engineering feat and a philosophical gesture. Detection must improve in parallel. To launch fast, we need early warning. Next-generation surveys like Rubin will spot more visitors earlier in their inbound arcs. If we gain years instead of months, intercepts become feasible, not desperate. Thus, astronomy and engineering must grow hand in hand. Exploration is not only about machines, but about imagination. Children hearing of Atlas may dream of touching such a comet. Artists may paint its coma, writers may invent stories of its long journey. Science inspires culture, and culture in turn supports the drive for missions. This cycle ensures that exploration remains a shared human effort. Safety again arises in discussion. Some wonder whether interstellar bodies could ever threaten Earth. The odds are small, but monitoring them with dedicated probes increases confidence and preparedness. Even if none pose risk, knowing their population is itself a form of planetary defense. Thus, science and safety align naturally in such projects. Interception could also extend beyond comets. Rocky asteroids from other systems may drift silently. Catching one would reveal not only ices, but alien rocks. Their mineralogy could tell us how crusts form in stars, unlike our Sun. Such missions would open geology to the scale of the galaxy. Think of it as fieldwork, only on a cosmic scale. Geologists hike mountains, collect stones, and bring them back to lab. One day, space probes will do the same, gathering grains from interstellar wanderers. It will be the most distant fieldwork humanity has ever attempted, and its return would be priceless beyond measure. Future generations may take this further. Instead of quick flybys, they may deploy orbiters around such comets. With advanced propulsion, probes could match velocity, hovering beside the nucleus. Instruments could map every vent, sample every jet, measure rotation directly. It would be Rosetta repeated, but for an interstellar stranger. Rosetta showed us cliffs, pits, boulders on Comet 67P. Imagine seeing such landscapes on a body from another star. Would the cliffs look the same, or would structures be alien, sculpted by different recipes? We do not know, but missions could show us real photographs of another system's ice. Now philosophy meets engineering. Exploration is not just technical, it is symbolic. To reach an interstellar body is to extend human presence beyond our star. It says we are not confined, not limited, but able to meet the galaxy's messengers face to face. It is as much about meaning as about data, as much about belonging as analysis. Belonging deepens when we act. Watching is passive, reaching is engagement. When we send a probe, we declare our part in the galactic conversation. We no longer wait for scraps to pass, we reach out to shake hands. This is the emotional truth of interstellar missions. Challenges will not vanish. Propulsion, cost, timing, detection. Each is real, each is hard. But so too were the challenges of flight, of orbit, of moon landings. Each was solved not by certainty, but by will, by daring to try. So too will interstellar intercepts become possible, step by step, decade by decade. Now Atlas itself will not be met. It is too soon, too fast, too fleeting for our current tools. But it is the teacher, the reminder that such visitors are common enough. And if they are common, then the chance to meet one is within our future. This realization sparks planning, funding, imagination, the seeds of missions not yet flown. Patience is again required. The galaxy is vast and opportunities rare but not absent. We must build readiness, keep probes waiting, keep eyes to the sky. The moment will come, and when it does, readiness will make the difference. The comet will pass, and this time we will not only watch. Let's drift into another corner of this narrative, carrying the vision of probes waiting like arrows, of sails catching light, of dust grains caught in aerogel. Exploration is not fantasy, but plan. Not myth, but blueprint. Next, we will turn toward the closing movement, how all these lessons, from chemistry to philosophy to exploration, fold together into the story of belonging to a galaxy seeded with fragments. And from that, we will learn what the final farewell of Atlas means for our own story as watchers under the sky. Outbound is the stage where every comet enters once its closest approach to the Sun has passed. For 3L Atlas, that stage is now underway, the faint nucleus moving farther from sunlight, cooling and fading from easy view. Its activity will decrease with distance, jets will weaken, and the coma that once spread brightly will shrink into a thinner veil. Astronomers measure this decline carefully because the rate of fading carries information about which gases still sublimate. Carbon dioxide dominated its inbound journey, venting strongly even at 3 astronomical units. That behavior marked it as unusual, different from most local comets that rely on water as their primary driver. Now, as distance increases, carbon dioxide vents close and water becomes the last major source. But beyond 2 astronomical units outbound, even water becomes weak, and activity shifts to minor traces. Photometry will show this decline as a smooth curve downward in brightness. Each night, the coma dims by fractions of a magnitude, tracking the steady fall of gas release. Dust grains once lifted remain in space, but they spread thinner and scatter less light. The tail, once distinct, becomes diffuse, blending back into the starfield background. Spectra confirm the story. Lines of carbon dioxide weaken first, then water, then perhaps faint signatures of organics, if any, remain. Instruments tuned to infrared will catch the last photons emitted by cooling molecules before they freeze again. From these curves, scientists reconstruct the thermal budget of the nucleus. the way its ices responded to sunlight. Dust analysis continues during the fading. Polarization curves evolve as finer grains dominate, the larger ones already dropped behind on slower paths. If porous grains fragment on their outbound drift, secondary tails may appear briefly before vanishing into the dark. Each observation adds another line to the record of how porous aggregates behave under interstellar conditions. Orbit refinements also continue. Now that the full arc of observation spans months, non-gravitational terms can be solved with higher accuracy. Tiny shifts from asymmetric jets are fitted into A1, A2, A3 parameters, stabilizing predictions of the object's escape route. Those numbers confirm the hyperbolic nature of the orbit and fix the final excess speed at infinity. Speed is the defining marker of its interstellar origin. No comet bound to the Sun retains positive energy once all forces are considered. For Atlas, the outbound velocity after accounting for every correction remains above escape, confirming its foreign birthplace. It will not return. It is already a permanent traveller outward, destined for another stretch of galactic dark. Trajectory now is set. From discovery images to outbound track, the orbit has been solved with confidence. Its perihelion passed safely at 1.3 astronomical units. Its closest Earth distance remained hundreds of millions of kilometers. No hazard ever existed, and now its outbound line is fixed, slowly separating it from the inner system. Systematic observation will continue as long as telescopes can hold it. Large mirrors in the southern hemisphere will stretch its track until magnitude pushes it below reach. Archives will fill with its spectra, images, and polarimetry, each tagged with date and geometry. Once it fades below limits, the record remains available for future generations to study. Study does not end with observation. Data will be modeled, reanalyzed, compared with Borisov, Oumuamua, and future visitors. Students years from now may extract new results from frames already taken, applying methods not yet invented. Thus, Atlas's contribution will outlive its visibility, continuing quietly through academic work. Population models gain strength from this addition. 3 detections in under a decade confirm that interstellar bodies are common, not rare anomalies. The inferred density of such fragments in the galaxy is far higher than older estimates. Billions must drift in the Milky Way, each one a remnant of planetary formation. Formation itself is the thread tying these studies together. Disks eject far more debris than they keep, scattering comets outward during early chaos. Jovian planets fling them with slingshot energy, removing them permanently from their parent stars. Atlas is one of those ejections, a fossil carrying its chemistry from that early violent era. Era of its formation is unknowable precisely, but clues exist. Its CO2 richness implies condensation in a colder zone beyond the water ice line. Porous grains suggest gentle collisions, not harsh grinding, so its nursery was calm and stable. From these hints, we infer it formed far from its star, in a belt of ices preserved in cold. Cold origins matter for comparison. Borisov was warmer, water-driven, similar to many solar system comets. Oumuamua was silent, perhaps processed to dryness. Atlas is colder, carbon dioxide heavy, porous in dust. Together they map a triangle of possibilities, showing the diversity of interstellar nurseries. Nurseries across the galaxy must therefore vary widely. Some produce dry shards, some wet comets, some rich in carbon dioxide, some perhaps with exotic volatiles. Each visitor we detect is a data point in that distribution, slowly shaping our galactic catalogue. The catalogue grows one object at a time, patient, cumulative, precise. Precise work is needed because each visitor is brief. Oumuamua lasted weeks, Borisov months, Atlast only a season. Every hour of telescope time must be used carefully, extracting maximum signal. Astronomy is built not on abundance of chances, but on depth of each single case. Case by case, the science expands. Polarization of dust, ratios of gases, rotation hints, non-gravitational torques. Each measurement is small, but small measurements across multiple comets reveal patterns that single ones cannot show. Thus, Atlast is not just itself, it is part of a comparative set. Set against that scientific framework, the outbound phase becomes as important as inbound. How quickly brightness falls, how dust changes, how jets shut down, each behavior is recorded. From that, we test thermal models, strength assumptions, and vent distributions. Even fading teaches, because fading curves reveal the interior. Interior models are not directly observed, but they are constrained. Thermal waves penetrate only centimeters per day, setting skin depths for heating. If activity persists longer than expected, it means deeper pockets of volatile material. If it fades quickly, it means shallow layers dominated the venting phase. Atlast's outbound decline will refine these models with interstellar context. Context is everything here. Local comets return, letting us test them again and again. Interstellar comets pass once, demanding we gather every possible detail. Each becomes a unique anchor point for theories, impossible to replace if missed. This is why Atlast was observed globally, by many teams at once. Teams across continents shared data, coordinating follow-up schedules. Professional observatories and amateurs both contributed, filling gaps when clouds covered one site. Together, they extended the arc, sharpened the orbit, deepened the chemical record. This collaboration is now the standard for such rare events. Events like this sharpen our vision for the future. Surveys will grow more sensitive, detections more frequent. The next visitor may already be inbound, unseen but present, awaiting discovery by the next wide-field scan. And when it comes, Atlast will be the precedent, the template for rapid coordinated response. Response will include not only telescopes but perhaps probes in decades to come. Comet Interceptor, waiting at L2, is one step towards such readiness. Future probes may wait, powered and prepared for the alert of a new arrival. One day, we may not only watch but intercept, sampling material from another star's nursery. Nursery chemistry will then move from spectra to laboratory tables. Isotopic ratios, mineral structures, organic complexities, all tested in detail, no telescope can match. Atlast reminds us of this possibility by showing what spectra can reveal, but also what they leave unknown. It is the stepping stone toward a deeper exploration. Exploration in astronomy often begins this way: quiet detections, patient study, then bold missions. Comets within our system were once faint smudges, now we have images of cliffs and boulders. So too with interstellar comets, faint smudges now, missions later. Atlast is one of the early smudges, its record part of the groundwork for the future. Future meaning is cumulative. Every fragment we study enlarges our understanding of the galaxy's material. We are beginning to see the Milky Way not only as stars but as debris, fragments, comets, shards. This material connects us to distant systems in chemical and mechanical truth. It is not speculation but observation, data written in spectra and curves. Curves are humble lines on a graph, yet behind them lies the life of another system. The carbon dioxide line is more than chemistry, it is a memory of formation zones. The polarization dip is more than scattering, it is a fingerprint of porous dust. The fading brightness is more than decline. It is evidence of how quickly layers exhaust. Each curve is small, but each carries the weight of galactic truths. Truths like these give astronomy its patient authority. We cannot visit other stars, but their debris visits us. We cannot sample distant disks, but their comets carry the recipe here. At last is one such recipe card, faded but legible, filed now in humanity's cabinet. In that cabinet, each visitor expands our reach without leaving our system. System by system, the picture grows. Local comets give us one perspective, interstellar comets another. The contrast shows which traits are common and which are exceptional. At last's CO2 signature is exceptional, but also valuable as a boundary point in the distribution. Boundaries define maps, and maps define our view of the galaxy. Galaxy scale is the quiet conclusion here. Not only are planets common, but so too are the leftovers they scatter outward. Our sky is crossed constantly by these silent messengers, most unseen. The ones we catch are enough to prove the abundance, enough to anchor the models. The Milky Way is seeded not only with stars, but with fragments, endless fragments. Fragments that endure for millions of years. They carry chemistry unaltered, grains porous, ratios preserved. At last has wandered for eons, untouched until now. For a few months, it was touched by sunlight, touched by telescopes, touched by human attention. Now it departs again, into the same silence from which it came. Attention is the final gift we offer. We noticed, we measured, we learned. The comet needed nothing from us. It would have passed unseen. But by watching, we gained connection, we gained knowledge, we gained perspective. That perspective is quiet, factual, and lasting. The galaxy is full of such wanderers. Wanderers will come again. Some will be brighter, some stranger, some faint. Each will add to the archive, each will shape the science. At last was the third, and its record now joins the ledger. The ledger is the real monument, not memory alone, but data, exact and repeatable. Repeatable science is what endures when the comet is gone. Spectra will be reanalyzed, orbits refined, models updated. Even 50 years from now, at last will still be cited, its lines appearing in papers. It will have long vanished from sight, but not from knowledge. This is astronomy's strength, permanence of record, even for transient events. Events like this close without drama. The comet fades, the observers move on, the archives rest quietly, but the effect remains. The sense that we touched another system's chemistry, that sense fuels future work, inspires missions, deepens the field. It is a subtle ending, but a strong one, like the closing of a measured experiment. Experiment is what each comet becomes, not one designed, but one offered. We accept it, measure it, and move forward. At last has been accepted, measured, and now it moves forward alone. We too move forward, but with more than we had before. That more is not philosophy only, but fact. Spectra, dust curves, ratios, numbers. Numbers do not stir crowds, but they stir science. They show excess speed, CO2 ratios, dust polarization. They confirm the interstellar nature, the cold formation, the porous texture. They show the range of what comets can be beyond our system. They are the ending words of at last's story, precise and lasting. Lasting is what matters here. The comet is gone, but its record endures. We will not see it again, but we will see its numbers forever. Its outbound path is silent, but our knowledge is permanent. That permanence is the true conclusion, the quiet ending of the narrative.